This video is brought to you by mywayteaching.com.
Dear students, in this part we are going to study about the fundamental forces in the nature. So before going to deal with these fundamental forces of the nature, let us take a very simple example to understand what is this concept of force and how it introduced. So we experience force in our day-to-day life in various ways. So we all have that idea of force, what this force is, isn't it? So you just take this very small example. Whenever we want to roll this ball on the ground, we need to push this ball, isn't it? So if we push this ball, then it will move to a certain distance. Again it will stop after that because of the frictional force of the ground, isn't it? We also feel force when someone pulls or pushes us. Thus, we experience forces in our day-to-day life in various ways. For example, one more example I can give here, like weightlifting. If I want to lift this, I need some force in my body, in my arm, so that I can lift this, isn't it? So everywhere we see this force, the concept of force in our day-to-day life. From such a rudimentary concept of force, now we are going to study about the scientific concept of force. So Isaac Newton is the person, or we can say Isaac Newton is the first who introduced the concept of force, okay, in his famous laws of motion. Not only in that, he also introduced the gravitational force. Okay, we'll study about this again, which is a very important force and it is a universal force. And in the macroscopic domain, besides this gravitational force, we may come across many different types of forces, isn't it? For example, we know like frictional force, as I told you just now, due to the frictional force of the ground, that ball will stop after moving a certain distance, isn't it? This, and then restoring force, we'll see it in springs, isn't it? Once when the shape of the string is when we push and when we leave that string, again it will come back to its original shape, okay, original position, and that is restoring force. Surface tension prevailing in the free surface of a liquid. So these all the liquids will be having this surface tension on the top of its surface, isn't it? So all these are the various kinds of force that we see in our day-to-day life. But in addition to this, force is also generated because of electrically charged and even from magnetic objects. Okay, force is also generated because of electrically charged bodies, I can say. Okay, electrically charged bodies. Okay, and and we also have other kinds of forces like nuclear forces. We know this, right? We know about this nuclear forces, intramolecular forces, nuclear fusion, nuclear fission. So all these are the examples of forces prevailing in the microscopic domain. So at present it is understood that even though we have thousands of forces, but basically it is understood that only there exist only four fundamental forces. How many? There exist only four fundamental forces. It is believed that all the other forces are the derived forces from this fundamental forces. All the forces are derived from this fundamental forces. Basic forces are four, and from those forces we can get all the other forces. So what are these four fundamental forces and what those forces says, all those things we are going to study now. So next, as I told you, all the forces in principle, these derived forces are all the forces which are derived from the fundamental forces. Okay, like the laws for derived forces are not independent of the laws of fundamental forces in nature. Okay, which means these fundamental forces are the basic forces and the derived forces are depending on the fundamental forces. Without fundamental forces, these derived forces cannot exist. They depend on these fundamental forces. I can give you an example of velocity. Okay, I can give you an example of this velocity. So we know that velocity is nothing but distance by time. Isn't it? Here, distance and time are the fundamental quantities. Okay. And this velocity is a derived quantity. So this velocity is depending on the fundamental quantities distance and time. So that is in the similarly derived forces also depend on the fundamental forces. So they completely depend on those fundamental forces. So as I told you, there are basically four fundamental forces, isn't it? And the first very important fundamental force is gravitational force. What is this gravitational force then? Yes, the mutual attractive force is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. So what is gravitational force exactly? See, we all know that whatever we throw from the ground, for example, if I throw a ball up, again it will come down, isn't it? That rain, okay, that rain, it also falls towards the earth, isn't it? Yes, all the fruits in the trees, whenever they fall, again they fall towards the ground. Why? Why it's like this? Why when I throw a ball it comes down? Yes, there is a force of attraction in the earth, and it is that force of attraction which is responsible for that ball to come down, for that rain to come down, and even for all the fruits they fall towards the earth because of that force of attraction which is exerted by the surface of the earth. So that is the gravitational force. And this gravitational force or this gravitational law, again it is introduced by the scientist, the famous scientist, that is Newton. And Newton says that every object in the universe attracts every other object in the universe. Okay, that is the law of gravitation. Whatever may be the object in the whole universe, it attracts every other object in the universe, and that is due to the force of attraction. So that gravitational force of attraction is nothing but that is attractive force that is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. So whenever we consider any two bodies which are very close to each other or which are at a far distance also, we can say they attract each other because of the gravitational force. As I said before, I can give you few examples. As I give one example is a ball, like when we throw it again, it will come down, isn't it? And even I gave you the example of rain. And if I want to give the example of celestial objects, then we can consider the planet system, isn't it? All the planets are revolving around the sun, and all the planets are there in their orbits, isn't it? They all the planets will be rotating in their orbits. Why? How it is that possible? Yes, all the planets are held by the solar system. The reason is the gravitational power of the solar system. Okay, because of that gravitational power of the solar system, all the planets will be revolving in their orbits. Okay, and this gravitational law, I will explain it with the example. See, here is the example. Here we have taken two bodies, like of masses m1 and m2. So these two are the masses of two bodies or two objects, we can say, and r is the distance. Okay, distance between these two objects. So this gravitational force or the gravitational law says that the attractive force F is directly proportional to the product of masses of the two bodies, that is m1 and m2, and it is inversely proportional to the square of the distance between them. So that is 1 by r square. So these two, by we know both the left hand side is f, so we can write it like this: f is directly proportional to m1 m2 divided by r square, isn't it? So this attractive force or the gravitational force F is directly proportional to the product of the two bodies, that is m1 and m2, and it is inversely proportional to the square of the distance between them, that is r square. So whenever we convert proportionality to an equation form, we get a constant, isn't it? So F is equal to G m1 m2 divided by r square. This G, will call it as gravitational constant. Okay, so actually this this G, it is called as universal gravitational constant, which means the value of G is constant throughout the universe. Okay, it is universal law. This law of gravitation is also called as universal law of gravitation. What is that universal means? It is acceptable throughout the universe. In every part of the universe, that law holds good. If you go to any part of the universe, not only world, any part of the universe, this gravitational law can be, this holds good. Okay, this gravitational law exists in all the part. Every object in any part of the universe attracts another object in the universe. So here in this figure also we can see the force F is shown, isn't it? And this force F is nothing but the attractive force or the mutual gravitational force, mutual attractive force between the masses of the bodies, that is m1 as well as m2. So this is the first fundamental law. So here we can see again the equation, that is F is equal to G m1 m2 by r square. This G, as I told you, the gravitational constant, not only gravitational constant, universal gravitational constant, and m1 and m2 are nothing but the masses of the two bodies, isn't it? The mass of one body is m1 and the mass of another body is m2, and the third one is r square, that is the distance between the two bodies, that is m1 as well as m2, and F is the gravitational force. In the coming part, we are going to study about the remaining fundamental forces.